Hello and welcome. In this video we are going to take a look at computing partial derivatives algebraically. So we've already discussed how to interpret them, and one of the common differences between working with derivatives in multivariable and single variable calculus is that when we're here in multivariable calculus, we treat the non-differentiating variable as a constant. So we compute derivatives in much the same way as we would in the Calculus 1 class, except now we're just going to treat the other variable that is not being differentiated with respect to as a constant. So the three most important properties that really hammer home why we're going to do things the way we do is these three properties here. So the derivative of a constant. So let's define C to be any constant we want, any real number, positive, negative, rational, irrational, integer, non-integer. The derivative, remember this is the derivative operator, so to take the derivative of a constant means that we get an output of 0. And so the way we can intuitively think about that is if you think about a constant, graphically, if something is constant, then its slope is always 0. So this has a slope equal to 0. And that doesn't matter what this constant is. Y equals a constant will represent a horizontal line. Now, when we take the derivative of a sum or potentially even a difference of two functions, so I'll put a plus or minus here because the derivative operator has this linearity property, meaning that if you're looking for the rate of change of the sum of two functions or the difference of two functions, then the result is going to be the sum or difference of the derivative of each of the two functions added or subtracted from one another. And another useful property is that if we have the derivative of some function, f of x, being multiplied by a constant, then what we can do is we can actually factor that constant out and take the derivative of the existing function, and then once we're done taking the derivative, multiply that constant back in. So this will help us insofar as we don't really need any other properties at the moment. Now we'll need to review some of the derivative properties or the derivatives that we typically take, like natural log, sine, cosine, tangent, all those guys, chain rule, product rule, but we'll touch on those shortly. So find all the partial derivatives of f of xy equals x squared plus y squared. Well, there are two of them. The first one being f sub x of x comma y. So as a recap, what that means is that we want to ask ourselves, how does this output, which we often refer to as z, how does z change when we change x by just a little bit? The other partial derivative that we'll have is f sub y of x comma y, and that is the same as asking, how does a small change in y affect the change in the output z? The two other notations that we can use here that are interchangeable is the partial of f with respect to x. So you can still read that as df dx. We just, again, use that partial operator to indicate that our function f depends on more than one input. That's all that the difference between df dx and kind of this partial f, partial x. They mean the same thing, but again, this is just used as a convention in multivariable calculus. Finally, this guy over here we can write as df dy. Also, we could say dz dx and dz dy, but since we're calling the function f, we'll just refer to the output as df. Okay, so to find these partial derivatives, all we need to do is think about taking the derivative with respect to x, or the partial derivative, I should say, with respect to x of the expression x squared plus y squared. Now, to compute that derivative, we see that we have a sum in here, and from our property of linearity of derivatives, we can apply the derivative to the first term, which is x squared, and to the second term, which is y squared, and then add the results back together. So we already know that the derivative of x squared with respect to x is 2x. That's by this one of our favorites, the power rule. Now, in the second term, we are treating y as a constant. So we need to point that out here. Y is a constant. Why is it a constant? Well, because in our derivative expression here, we're saying we want to observe how does the output of this change when we only vary x. We're not going to vary y, so we hold it as a constant. So we can think about if y is a constant, then y squared is also a constant. And so this is no different than just writing the derivative of c. This whole thing in this box is a constant, and the derivative of a constant is 0. So we get plus 0 over here. And that refers back to property 1 here, that the rate of change of something that is constant is 0. It doesn't matter if you square a constant. If you square a constant, it still is constant in its own right. So that completes our derivative here. So as a conclusion, we could state that f sub x of x comma y, the derivative of f with respect to x, is simply 2x. And we'll repeat the same thing over here, but when we apply our derivative operator, it's going to be with respect to y. So you might be able to guess that in this context, we're allowing y to change, and therefore x is constant. And therefore any function of x is going to be constant, and involving only x. So if x is constant, then the square of a constant will also be constant. And rather than having to write out all these extra steps here, it is okay to say, well, the derivative of x squared, or the derivative of a constant, is 0, and the derivative of y squared with respect to y is 2y, which leads us to the conclusion that f sub y of x comma y is equal to 2y. And so these are our two partial derivatives. Now, they may not always look like this, where you look at them and you say, oh, so if the derivative with respect to x is 2x, then the derivative with respect to y must simply be 2y. And that's not always the case. That just happens to be that both of our variables are squared in our f of xy function. Now let's take a look at a more dynamic looking one. Here again, we're going to have as many partial derivatives as we do input variables. So all we need to do is look at how many variables are there in our equation. There are 2. Therefore, we're still going to have the partial with respect to x of xy. And again, you could write that as df dx. So what we want to do is we want to take the derivative with respect to x of the expression x times y squared plus 2x cubed times y. Now, I always like to make myself a note before I take these derivatives, especially as you're getting started, that here we're holding y constant. Why is that the case? Well, once again, we're asking how does f of xy change? How does the output change when we only vary the variable x? Well, by virtue of that statement alone, that means we're holding y constant. So I'm going to just create little boxes in here to indicate all of the things in each of these two terms that is constant. So if y is constant, y squared is constant. Okay. Same thing over here. If y is constant, then that's a constant right there, as well as this 2 is also a constant. So what I'm going to do is when I take, because this is x times multiplied by a constant, when I take the derivative of this term, I'm going to be able to factor that constant out. And that results from property 3 here, that the derivative of a constant multiplied by a function is equal to the constant multiplied by the derivative of the function. So with that being the case, as I distribute this derivative in, what I'll be able to do is take the derivative with respect to x of x. Now this is times y squared, but we've already said that y squared is a constant, and therefore I'm going to factor that y squared out, and I'm left with just taking the derivative of x. Now I can't say that this is equal to 0 because that is only the case when you're taking the derivative of a constant by itself. If it's a constant not multiplying a function of the variable, then its rate of change is 0. But we cannot say that the derivative of a constant multiplied by a function of x is 0 because this is a function of x. So as you change x, this is bound to vary as well. Okay, so that means I'm going to go ahead and take the derivative of the second term as well. And in the second term, I'm going to leave myself a little bit of space here. This is with respect to x. Now x cubed, that's a function of x, but we've already established that 2 and y are both constants. Now this is 2 times x cubed times y, so I really have 2 constants here that can get factored out, and those are going to be 2 times y. So this is still 2 times y times x cubed, times the derivative of x cubed. I could put the 2y back in there, but I'm going to factor them out because I don't have to worry about them until I've taken my derivative. And so we know that the derivative of x with respect to x is 1. That's a linear function of slope 1. So we'll just have y squared times 1, or just y squared, plus 2y. The derivative of x cubed is 3x squared, so this will be plus 2y times 3x squared, which could be more compactly written as y squared plus 6yx squared. Or you could alternatively write it as 6x squared y, and that's completely up to the user. Now what we've just calculated here is this is the partial derivative of f with respect to x. And that completes our derivative here. Now for the second partial, which we're now going to do, f sub y of xy, again, just alternatively can be written as df dy. We're going to take the same derivative, but now our variable of differentiation is going to be y, and we're taking the derivative of xy squared plus 2x cubed y. Now again, these are all multiplications here, x times y squared, 2 times x cubed times y. So in this situation, we are holding x constant, and since x is constant, we're going to treat it as such. So that means this is a constant times y squared. 2 is a constant. If x is a constant, then the cube of a constant is constant, and 2 times a constant is also a constant. So I'm going to put this whole expression here, or this whole coefficient in a box. And so as I apply my derivative operator, I'm going to have the derivative of y squared with respect to y. Now since this is a constant times y squared, I could factor that constant out. For my second expression, I'll have plus the derivative with respect to y. Since this is a constant times a variable of y, I can factor out that 2x cubed. And I will leave my y in there. So the derivative of y squared is going to be 2y multiplied by x will give me 2xy. The derivative of y is 1 with respect to y. It's just like the derivative of x with respect to x. And so that derivative will be 1, which will leave us with 2x cubed times 1. And that's a perfectly fine way to leave it. And so that is our partial of f of xy with respect to y. And so now we have our two derivatives, our derivative with respect to x right over here, and our derivative with respect to y right over here. And that completes the partial derivatives of this function. Let's do one more before we address some of the differentiation formulas that we're used to from our previous calculus course. Here, we want to compute f sub x, or in other words, the derivative of f of xy with respect to x, alternatively written as df dx. And you can see I'm really emphasizing that there are multiple notations that we can use here. And which notation you use is really dictated by the context and what source you're using. So we're going to take the derivative with respect to x of y times sine of x plus x times cosine of y. And once again, as you get more and more comfortable with this, you may begin to see the pattern. Okay, so anything that contains a y is going to be treated as a constant. Therefore, if y is a constant, so let's pretend that this were to be the cosine of pi. Well, the cosine of pi is a number. That's asking us what is the horizontal component of the right triangle when our angle is pi radians. And one of the things we may notice here is that this is going to end up equaling -1. And so that's going to be a constant. So y is a constant, then cosine of y will be a constant as well. So now we can apply that same principle. We're going to factor out the y, the derivative with respect to x of sine of x, plus factor out the cosine of y, because remember that's a constant, times the partial with respect to x of just x. And so again, this is our constant, and this is our constant. And the derivative of sine of x is, you may remember, cosine of x. So y times cosine of x. The derivative of x is 1. Cosine of y times 1 is just plus cosine of y. And so this right here is our final function, the partial of f of xy with respect to x. And now we're going to repeat this same process, but we're going to apply it now to f sub y of x comma y. So the derivative of f of xy with respect to y, just df dy. And so now we're going to take the derivative of the same expression. And now anything that contains an x is going to be a constant. So I have sine of x, that's going to be a constant. X is going to be a constant, and so those are the coefficients I'll be able to factor out when I apply that partial derivative. So I'll have sine of x times the partial with respect to y of y plus x times the partial with respect to y of cosine of y. So once again, here are the constants. And the partial of y with respect to y is 1. So this will leave us with just sine of x times 1 plus x times cosine of y. Well, cosine of y, its derivative, is going to be negative sine of y. So this will actually be plus, or rather minus x times the sine of y. And this is what we're calling f sub y of x comma y. You can see that really the only difference in computing these derivatives is we have to identify the constants first. As you are getting acquainted with this process, it will be probably helpful to create some sort of system so that you know exactly what is constant and what is not. Now, our old differentiation rules apply much the same way here. So this rule here, this is the second one that we looked at, the second property, which is the derivative of a sum or a difference, is the sum or difference of each of the derivatives. Here's our constant times a function. Its derivative is, you can factor out the constant, take the derivative of the function, multiply them back together. The product rule, when you have a product, now the important part here to note is that this is when two functions containing the same variable are being multiplied together. So if you look back at what we have here, this may seem like you have to apply the product rule, but notice that y times sine of x does not reuse the same variable. So it's not a product of two functions containing the same variable. In our case, it turned out that one of the variables is being held constant. But when you have a product of two functions containing the same variable, then you do have to apply the product rule, and that's going to be f prime times g plus f times g prime. Of course, the quotient rule, function divided by another function, f divided by g, its derivative is f prime g minus f g prime, divided by the square of the denominator. And this is the chain rule. We'll take a look at an example with the chain rule. If you have a function within a function, then you can take the derivative of that inner function and multiply it by the derivative of the outer function. And some of these are going to look familiar. The power rule, derivative of e to the x, the derivative of an exponential function where the base may not necessarily be the constant e, it could be like 2 to the x. So the derivative of 2 to the x would be 2 to the x times the natural log of 2. Derivative of natural log of x, 1 over x, sine, cosine, tangent. And then arcsine and arctan are listed here, but those are some of the more less common ones that we want to differentiate. As far as the chain rule is concerned, this formula I don't find to be incredibly helpful. I prefer to use a version of the chain rule, which we will soon encounter, but that seems to make much more intuitive sense. And that is that if I want to find the derivative of a function. I'm just calling this p to distinguish it from, a lot of times we'll have y and x in our equations, and so if we are using the chain rule to take the derivative of just some term within that entire function, then it's just helpful to assign it a variable name. So if I want to find dp dx, then I can actually create a series of multiplications of derivatives that will cause the units to cancel out and produce dp dx. So let's just, for the moment, observe that we know that the derivative with respect to x of the natural log of x is 1 over x. So we already know how to take the derivative of a function like that. But in this case, we don't have the natural log of x, we have the natural log of some function of x. And so what I'm going to do is I'm going to refer to this stuff inside of the what we often call the argument of the natural log. I'm going to refer to this as u. And now my function really becomes p equals the natural log of u. And u is equal to 3x squared plus 22x. Now the reason I substituted that in there is because natural log of u looks a lot like natural log of x. It just has a different variable in its place. So p is a function of u, and u is a function of x. And as we'll learn later with the multivariable chain rule, if you take the derivative of p with respect to u, and then you take the derivative of u, this second guy here, with respect to x, and if you multiply them together, you can see that the du's cancel, and what you've really computed is the derivative of p with respect to x. So now I can apply that. So dp du, the derivative of p with respect to u, well, now I'm differentiating and treating u as the new variable, and that's just going to be 1 over u. And the derivative of u with respect to x is now just taking the derivative of the right-hand side, which is 6x plus 22. Now I got to put it all back together, because what I wanted was dp dx. So we will write dp du, which is 1 over u, multiplied by du dx, which is the quantity 6x plus 22. Now 1 over u, now I really wanted the derivative of p with respect to x. Now I have two variables in here, so the last step is to replace u with what it is equal to in terms of x, which is 3x squared plus 22x multiplied by 6x plus 22. And short of doing simplifications and that type of thing, this is really our final answer. Sure, we could perhaps maybe factor out a constant, but I don't think that's going to get us very far. So this is in fact that derivative. Now in terms of the formula that you often see, which is this format, g of x is being treated as a brand new function. So when we think about p of x being the natural log of 3x squared plus 22x, we can really think about this as, in that notation, what they're calling g of x. So if you take the derivative of p with respect to x, then you're going to take the derivative of the natural log of g with respect to g. So the natural log of g, its derivative would be 1 over g. Then the chain rule requires us to take the derivative of g of x and multiply that by the derivative of f with respect to g. And the derivative of 3x squared plus 22x, you can see it's just going to be 6x plus 22. And lastly, making our substitution, you see that we get exactly the same result as if we had done it in the differential operator form. And I prefer this format here because it allows me to make any substitutions to simplify the function I'm trying to differentiate. And so I create some sort of substitution to make it look like one of the base functions in our derivative sheet. And then I can reconstruct and multiply the derivatives back together to formulate the derivative I'm looking for. So for instance, if you had, we'll take a look at one more example here. Let's say that we wanted to take the derivative of we'll call this dw dx, where w is equal to, let's say, the natural log, or let's pick something else here. We'll go e to the natural log, how about maybe let's do cosine of 3x squared. So in this case, we notice that this does not look like one of the derivatives in the derivative formulas, but I can see it is an exponential. It does have an exponential function. It's e raised to a power, but that power is not x, it's the cosine of x. So in this case, to make it look more like that, if I let u equal cosine of 3x squared, then that implies that w is going to equal e to the u. And since I want a dw dx, well, out of this expression, u equals cosine of 3x squared, I can really describe that as du dx, and the derivative of cosine of 3x squared is going to be negative cosine of 3x squared multiplied by the derivative of what's on the inside, which is 6x. And I can also compute dw du, which is, well, the derivative of e to the u with respect to u is just e to the u. Well, we can see we were able to apply one of the formulas. Now here we kind of used another chain rule without calling it that. So you could again make a substitution and say, well, I don't know how to take the cosine of 3x squared, but I do know how to take the cosine of x. And we could make another substitution, and instead of calling this 3x squared, we could call this v. But let's try it both ways and see what we come up with. So in this case, we notice that if we multiply dw du by du dx, once again the du's cancel, I get dw dx, and the product of those two functions is negative cosine of 3x squared times 6x times e to the u, where u is the cosine of 3x squared. And as just a little aside, kind of mentioned we could use two iterations of the chain rule. We said we had w equals e to the cosine of 3x squared, and we saw that if we let u equal 3x squared, cosine of 3x squared, that would allow w to be equal to e to the u. Now I can see that I can already take the derivative of w with respect to u based on using the derivative of an exponential function, but we've observed that cosine of 3x squared is not a derivative that we have up here. In fact, we only have the option of taking the derivative of cosine x, which is negative sine of x. So in order to use this, I would have to make the argument of cosine to be a single variable instead of a function of that single variable. So to show how we can use the chain rule in multiple steps, now, because I can't yet take the derivative of u, I can take the derivative of w now, I can also say let v equal 3x squared. Let v equal 3x squared. So that would then imply that u is equal to cosine of v. So now I have three functions. I'm going to go ahead and star those. I'll go ahead and highlight them here. I have w equals e to the u. I have v equals 3x squared. And I have u equals cosine v. Now I know how to take the derivative of each of these three functions. This is a power rule. This is the derivative of cosine. This is the derivative of an exponential. But what I've done in effect here is for dv dx, or for v equals 3x squared, I can compute dv dx. For u equals cosine v, I can compute du dv. And for w equals e to the u, I can compute dw du. And so if you look at what happens here, here we wanted to we ultimately wanted to compute dw dx. So let's see if we've accomplished that task by putting together these three derivatives. Well, dv cancels here and here, du cancels here and here, and what I'm left with is dw dx. So I get dw dx. And that results from multiplying the derivative of these three functions together. So dv dx, the derivative of this is going to be 6x multiplied by the derivative of u with respect to v. The derivative of cosine of v is times negative sine of v. And dw du, the derivative of e to the u, is just e to the u. And so now I can multiply these three things together. Ultimately, I do have to replace v with, so this will be times negative sine of v, which is 3x squared, times e to the u, where u is the cosine of 3x squared. So e to the cosine of 3x squared. And you can see that we get exactly the same derivative as we obtained here, except I did not compute the derivative of cosine correctly. I apologize for that. This should be negative sine, and this should be negative sine as well. So now you see that we do have the same function. We have 6x here, we have a multiplier of 6x, a negative sine of 3x squared, and an e to the cosine of 3x squared. I apologize if this is kind of a roundabout way of doing it, but if you do need to do chain rules within chain rules, this may be helpful, and you keep making the substitution. It's sort of an art form. You kind of keep doing it until you're able to have functions that only contain something that we can apply the power rule to, or the derivative of a cosine, or the derivative of an exponential. So this is just an alternate strategy. And if you're good by looking at functions and being able to grab the pieces necessary, then you can really get away with something more simple like this. All right, so we'll look at a couple more examples with using the product rule and the chain rule applied to these multivariable functions. So the partial derivative of this guy here, so we're going to grab f sub x of x comma y. And to do that, we see first of all that we do have a product, and that product contains two functions of x. So here we have some sort of function of x, here we have some other function of x. Now we're not going to have to apply the chain rule here because we see that if we take the derivative of this with respect to x, e raised to a constant power is going to be a constant. So here we only have to take the derivative of the natural log of 2x. All right, let's get to work. So the partial with respect to x of x squared times sine of x. And then we're also going to take the partial derivative of the second term, and I can factor out that e to the 3y because it is a constant, and just take the derivative of the natural log of 2x. So there's our constant. Now here I have to apply the product rule because I have a product containing product of two functions both containing the same variable x. So the product rule is the derivative of the first piece, the first function, multiplied by the second function, no derivative taken. Add to that the the original first function multiplied by the derivative of the second function. So there's our application of the product rule that we had to apply to just this first term. For the second one, we get to use the chain rule. This is e to the 3y multiplied by, let's see, the natural log, and the derivative of natural log is 1 over the argument. So the natural log of stuff will be 1 over stuff, times the derivative of the stuff, which is the derivative of 2x. In this case, that equals 2. We're not going to simplify any further at this moment. We have completed the derivative. To compute f sub y of x comma y, you might think again that we need to use the product rule here, but the whole first term, as we write this out, the derivative with respect to y of x squared times sine of 2x, well, this is just going to be 0, because if x is being treated as a constant, then x squared is a constant, the sign of 2 times x will be a constant, and the multiplication, or the product of two constants, will also be constant. So this whole thing here is just one big constant. And you can see how changing the variable of differentiation makes a world of difference in terms of the difficulty of computing those derivatives. For the second term, natural log of 2x is going to be a constant, so we can factor that out, times the derivative with respect to y of e to the 3y. And so once again, natural log of 2x is a constant. So the first term will be very easy to take the derivative of. The rate of change of a constant is 0. And then we have the natural log of 2x. The derivative of an exponential, now this is e to the u, so e to the stuff, the derivative of e to anything is going to be e to the anything, multiplied by the derivative of the stuff, so the derivative of 3y with respect to y will be 3. And we end up with the natural log of 2x, this is multiplied by, natural log of 2x, or 3 natural log of 2x e to the 3y. And that completes our derivative there. Now the quotient rule is not really going to be much different. The quotient rule you're going to have to apply in instances where there is a fraction, but where you cannot simply cancel things out and remove the fraction. So in this case, we see that we're going to need to use the quotient rule. Now, the important part here, though, is that both f sub x and f sub y will require the quotient rule, because the quotient rule states that if you have a ratio of two functions that both contain the same variables, and you're taking the derivative with respect to that variable, then you do need to use the quotient rule. So if we change this to a function of y divided by a function of y, you can see that both the numerator and denominator would contain that variable, and therefore that would require an iteration of the quotient rule. So to compute f sub x of x comma y, we're going to need to take the derivative of the top with respect to x, multiplied by the bottom, no derivative of that. So this is like thinking about this as f over g. F prime would be this times g minus the top, no derivative, multiplied by the derivative of the bottom, all divided by the bottom squared. And so the derivative of x to the fourth times y, well in this case we could factor out that y, and the derivative of x to the fourth is 4x cubed. So we would have 4x cubed y times x minus 2y, that's just this parenthetical expression, minus x to the fourth times y. Now the derivative, here we can apply the linearity of the derivative. The derivative of x is 1, so this will just be 1. The derivative of negative 2y with respect to x will be 0, because that's a constant. So we can just really remove that in its entirety, since its derivative will be 1, all divided by the bottom squared, x minus 2y quantity squared. Now to get the second partial, with respect to y, we'll apply the same principles. Again, we see that there's a y in the numerator and denominator. If there wasn't a y in the denominator, let's just say it was just x to the fourth y over x, well, first of all, you could cancel out one of those x's, but secondly, the derivative with respect to y would not require the quotient rule, because the quotient rule is only used when the variable you're differentiating with respect to is found in both the numerator and the denominator. So we need to take the derivative of the top with respect to y, so x to the fourth y, multiplied by the bottom, x minus 2y. You can see that the setup is identical, except that we're now differentiating with respect to y. Also, if you have a hard time seeing this, about when to use the quotient rule, I mean, you could, in theory, use the quotient rule anytime you see a fraction. A lot of times you're just going to go through more work to do it, but hey, there's nothing wrong with that. And now this is going to be minus the derivative of the bottom with respect to y. Actually, x to the fourth y times the derivative of the bottom. And that's going to be with respect to y of x minus 2y, still divided by the bottom squared, which will be x minus 2y, quantity squared. Now the derivative of x to the fourth times y, with respect to y, x to the fourth is a constant, so we could factor that out, and that would leave us with x to the fourth times the derivative of y, which is x to the fourth times 1, or just x to the fourth, multiplied by the denominator unchanged, minus x to the fourth times y. Apply the linearity of the derivative, so the derivative of x with respect to y is 0, and the derivative of negative 2y with respect to y is negative 2. And this is again all over x minus 2y quantity squared. You can do some simplification, but this concludes the derivative itself. Now before we move on, before we stop, let's go ahead and take a look at an application. We have a vibrating guitar string, which is originally at rest along the x-axis. So imagine this x-axis to be the string that is exactly 1 meter long. So it has a point of attachment here, it has a point of attachment here, and when you pluck that string, it's going to start to vibrate up and down. So x is the distance in meters from the left end of the string. At time t seconds, the point x has been displaced, y equals f of x comma t. Now be careful here, y is what we're calling the output variable, so we have y, which depends on two things, x and t. X is the displacement. It's going to be measured in meters. T is a measure of time. That's going to be measured in seconds. And y is going to be how many meters above or below the rest point this string is in its oscillation. So this is kind of like vertical meters. But again, that's going to be measured in meters. Recording these units is helpful so that we can see that as we compute derivatives, like, for example, dy dx, well, if y is going to be in meters and x is in meters, then this is going to be in meters of height divided by meters of distance. So it'll be meters per meter. You can't cancel those out because these are different distances. One is along the horizontal, one is along the vertical. And here we'll also have dy dt, and this will be in units of, y is in meters of height, t is in measure of seconds. So this can be thought of as how fast the string is oscillating at any given point. So at time t seconds, the point x has been displaced that many meters vertically from its rest position. That's the up and down. How far up and down that string goes depends on how far we look from its left end point. Of course, here you're not going to have as much fluctuation because that's really close to where the string is attached. So it can't really oscillate much up and down. But the oscillations in the center are going to be kind of bigger, and the oscillations towards the other end point are going to be really small, and everything in between. Now these three curves that we see here are just the height of the string at a different position. So this notation is what is the height of the string at a distance of x meters. So let's call this distance here, we'll call this x meters. So here we are, right there. That's a distance of x meters. And at a distance of x meters, at time 2, we see the string is at a higher point than where it was at time 1. And then at time 10, it looks like the string has maybe bounced up and down a few times, and at that moment, the string is actually displaced negatively away from its rest point. So evaluate f sub x of 0.3 and 1, and f sub t of 0.3 and 1. Now, just as in Calculus 1, we can't do any substitutions until we've taken partial derivatives. So let's start with that. So to take the derivative of f of x t with respect to x, the derivative of, with respect to x, of 0.003 sine of pi x times sine of 2765 t. And since we're taking the derivative with respect to x, anything that does not contain an x in it is technically a constant. So 0.003 we can factor out. Sine of 2765 t we can factor out because it doesn't depend on x. So this will be analogous to taking the derivative of, or 0.003 sine of 2765 t times the derivative with respect to x of sine pi x. That will equal 0.003 sine of 2765t, and now this will be cosine of pi x. The derivative of sine of stuff is cosine of stuff, multiplied by the derivative of the stuff. So this is not just sine of x, this is sine of pi x, and the derivative of pi x is pi. So we have our partial derivative there. That's our f sub x. And so now to compute f sub x of 0.3 and 1, what we need to do is we need to insert 1 in for t and 0.3 in for x. And when we do that, we're going to come up with 0.002. Now, in terms of the units that we've established, we said that the derivative of the function with respect to x is going to be in units of meters per meter. Now, if I put this over 1, it's going to be a little bit easier to see. 0.002 meters of height per 1 meter of distance. So if we think about what this means that at a distance of 1, or sorry, at a distance of 0.3, which is somewhere in the middle here, right about there maybe, that if currently we look at a distance of 0.3 meters from the left, after 1 second, the height of the string is changing by 0.002 meters for every additional meter of horizontal distance. Okay, so if we're basically at this point right here, so at time 1, so that this would be the curve at time 1, that essentially what would happen is if I'm at that moment in time where the string is basically freeze-framed, and the string looks like this in that pausing of the video, that basically if I were to go over 1 full unit this way, which of course would take us past the string itself, but this is just a ratio. So if it's 0.002 meters for every additional 1 meter, then it would be 0.001 meters of additional height for every half meter. So I should expect that the slope of that string right there, the slope of that string has a slope of 0.002. And all that means is that basically the string is growing higher as you move further to the right. So going further to the right will increase the height of that string a little bit more. So I'm sure if we were to plug in something like 0.7 instead of 0.3 for the distance, we should get a negative derivative, which would be indicating the slope of the string over here is actually a negative value. Now we can repeat this process for the second derivative as well. And if we did that, now we would have, let's see if we can write this out without going through the process. The derivative with respect to t of f of x comma t is going to equal, it's going to be 0.003 times the cosine of pi, oh no, excuse me, that'll still be sine. Sine pi x, because x is constant here, multiplied by the derivative of sine of 2765t, which would be cosine of 2765t, multiplied by the derivative of the stuff, which is 2765. And we should again I should also point out that we have to be in radians here. The only time you're going to be in degrees is when the problem is explicitly in degrees. And now I can make my substitution. 0.3 for meters, 1 for or 0.3 meters of horizontal distance at time 1 will come out to 6.18. And we've already established that the derivative with respect to t will be in meters per second. And so I can interpret that to mean that basically if you look at these two strings here, or these two moments in time, the lower curve here is at time 1 and the higher curve here is at time 2. So what we can distinctly see is that as time is passing beyond time 1, the string is traveling upwards. The string is traveling upwards. Now this is meters of height. So this just means that at this moment in time, at a distance of 0.3 meters from the left, after 1 second, the height of the string is changing by 6.18 meters per 1 second. So I'll just kind of summarize that. I'll say at the given time, given distance and time, the string is traveling upwards at a speed or at a velocity of 6.18 meters per second. And so at this point we've established a lot of our derivative rules working with multivariable functions, and we can see that now the applications that we were exploring in the previous video, the mathematics there still applies, but the difference here is that now we actually get to compute those derivatives given the functions, and then we can interpret their result.